So section 2.3 is called falling objects. What we're going to do today is we're going to take a look at the vertical motion of an object, but it's still going to be one-dimensional. So imagine if you were standing on a diving board and you just kind of like fell into the pool. You didn't jump. You just dropped off the end of the diving board straight down into the pool. We're looking at objects like that. Or you toss a baseball straight up in the air and it returns straight to your hand. But again, we're not looking at an object in projectile motion where you launch at an angle, but straight up and straight down. The three objectives are going to be to relate the motion of a free fall object having constant acceleration, calculate the displacement, velocity, and time at various points in the motion of the fall, and to compare the motion of different objects in free fall. First, we need to define what free fall is. It's the motion of a body when only the force due to gravity is acting on the body. So for example, if an object is to fall off the end of a table, what's pulling it to the ground? Only gravity. There's nothing else acting on it. So that's what we call free fall. There's no external forces besides gravity acting on it. Now realistically, the force of air resistance, or what's called force of drag, is acting on it. But for the simplicity of the class we're looking at now, what we're going to do is we're going to take the assumption that air resistance has no effect on the problem, or it is negligible. So the example that you see here is an object being thrown up in the air, a pool ball, for example, and coming right back down. Now, this graph actually corresponds to the motion of this object. Now let's talk about what happens here. When you throw an object upward, it's got some velocity initially. Until it gets to the top, then what happens? It pauses for an instant in time, and then it starts to return back to the ground. So if I were to trace this here, I would say it's got a positive velocity, but it's slowing down. So the velocity is getting lower and lower and lower until the velocity is zero right up here. Then it starts to fall to the ground. Well, when an object falls to the ground, its velocity is negative. So that's what you're seeing on this graph here. So here, the object is launched up. It starts to slow down, it starts to slow down until it gets to the top of its path, and it stops for an instant of time, which means velocity is zero. It stops right there. But then the object continues to fall to the ground or to the surface of the earth, so it picks up speed but in the negative direction, thus negative velocity. So the velocity increases but in the downward direction, so the velocity keeps increasing but negatively it increases. Notice, if you will, that the slope of this graph is always negative for a specific reason. The slope of a velocity versus time graph is defined as acceleration. Well, what's the acceleration here? The acceleration is gravity. And the acceleration is pulling down to the earth. Gravity always pulls you down. So the acceleration of this line, or its slope, is simply the gravitational acceleration, which happens to be little g. Now, little g is just our constant we use in physics to represent negative 9.81 meters per second squared. Now, some other fun facts to note here. First, negative 9.81 meters per second squared is the acceleration of gravity on Earth. Because of Earth's mass, this is what the gravity is. Simply said, the moon has about, well, let's say the moon, for example here, has 1/6 the gravitational pull of the Earth. So its gravitational constant might be something around like 1.5 or 1.6. So depending on the planet you're on, it's going to change because the mass of each planet is different. In addition to that, really, if you change elevation on the Earth, it also changes the acceleration, but we're going to assume that everything is on sea level. So this is going to be the acceleration of gravity that we're going to use for the rest of the year on Earth. And if you look at your formula sheet on the bottom for constants, this is the first constant that we have listed. Okay, let's take a look at example 1 here. An object is dropped from the top of the Empire State Building, which is 443 meters tall, and lands directly below on the ground. Determine the velocity of the object when it makes contact with the ground, and call it the impact velocity, and how long does it take to reach the ground. So let's start with our givens. First, we know the height of the actual building right there. We know that it's dropped from rest, so we know the initial velocity. We also know the acceleration due to gravity. So in this problem, what we can do is we can start by saying that the acceleration due to gravity on Earth is just g, which is negative 9.81 meters per second squared. The next thing we're going to write down is the height of the building, but since it's falling downward from the top of the building, it'll be y equals negative 443 meters. Finally, because it's dropped, we know that there's no initial velocity, so that's going to be simply 0 meters per second. With those three pieces of information, we can go about solving this problem. So the first thing we want to do in this problem is say to ourselves, well, what formula are we going to use? Well, what are we looking for? It says determine the velocity of the object when it makes contact with the ground. So that's like our VF, when the object hits the ground at the very end of the problem. So we're looking for VF here. Now, if we're looking for VF and we've got all the other piece of information here, we could start by saying, well, there's no time involved yet. At the end, we're going to search for the time. How long does it take? So without time, the only formula we can really use is the following. Now remember that in this problem, when we see y here, it's the same thing as x. We talked about x being the horizontal displacement in the past. Now we're taking a look at the vertical displacement, and that will be y. So what we're going to do next is we're going to take our look at our equation here and realize what we're solving for VF, but VF is already known. It's given right here, so we see that we have it. So let's just go ahead and plug in these numbers and then take the square root. So we have VF squared equals, this is 0, drops off, so it's 2 times A times Y. That information tells us that if we go ahead and take the square root of the answer that we get from that product, we'll end up getting negative 93.2 meters per second. So this is the impact velocity, or simply the velocity as soon as the object, or the instant before the object, hits the ground. Next it says to say, how long does it take to reach the ground? So we're looking for time now. How long does it take to reach the ground? So we're looking for time in this part. Since we're looking for time, we could think about, oh, we know VF now, so now we can use VF equals VI plus AT, because we know everything. Earlier we did not have VF, so we couldn't have used this to find time. But now that we found VF right here, we can figure out what it is. And what we'll notice is that, again, this goes to 0 because there's no initial velocity. So let's go ahead and solve for time. We have VF equals AT. We'll have VF over A is equal to the time. So let's go ahead and plug in now. The final velocity was negative 93.2 meters per second over the acceleration of negative 9.81 meters per second squared. And clearly they're both negative, so that we get a positive time. And this turns out to be a time of 9.5 seconds. The alternate solution here is to use x or y equals VIT plus 1/2 AT squared, realizing that the VIT drops off, and you could then solve for t. But again, you'll get the same answer, no difference. Example 2 says a toy rocket is launched with an initial velocity of 25 meters per second straight up. So here's the ground. Okay, here's the rocket on the ground. It gets launched straight up. It says, after how much time will the rocket reach max height? Well, here's what we have to think about. When the rocket reaches max height, it's up here. So we have to think about this problem in parts. We're not thinking about the problem as if it's launched and comes back to the ground, but simply if it's launched and it stops at max height. So we're looking at like the first half of the problem. So we're making this into like a, you can make the analogy that it's a piecewise function, or it's broken up into little parts. Okay, so what we have here is an initial velocity of 25 meters per second, and that's positive because it's upward. We know that it comes to rest when it gets to the top, so that means that the final velocity has got to be 0. Again, I know it's tough to put or wrap your head around it here at first, but the final velocity is the point at which it stops, because we're only looking at the first half of the trip where the rocket leaves the ground up to the top. We're not worried about on the way back down yet. That'll come up in the next few parts. We know the acceleration is negative 9.81 meters per second squared. And in this part, we're looking for how much time it will take the rocket to reach max height. Well, given these variables, we could start by using our first kinematic equation, VF equals VI plus AT. Solving for t, we can move VI over, and we can divide by A. And that's our generic solution for time. At this point, all we have to do is plug in what we know. Well, we know that the VF is 0. I'm going like this. We know that VF is 0. We know that the VI in this problem is 25. So 0 minus 25, all over, and that's meters per second, all over negative 9.81 meters per second squared. Okay? And that's what time is equal to. So really, what are we looking at? We're looking at the negative 25 over the negative 9.81, which turns out to be a time of 2.55 seconds. Part B says, what is the rocket's maximum height? So the same problem again, but now we're looking for the value of y. Well, if we have the same problem, we should go about solving it pretty much the same way. Think of this now, again, only as the first half of the trip, or the first leg of the trip. So now we have to say, let's use the equation Vf squared equals Vi squared plus 2ay. And we want to solve, in this case, for the value of y. So we have to do a few things here. First, we need to move over the Vi squared, and then divide by the quantity 2a. So let me write it a little bit lower to show the lines. So we have Vf squared minus Vi squared equals 2ay, and then dividing by 2a, we get Vf squared minus Vi squared all over 2a is equal to the value of y. Okay, notice that we have Vf, we have Vi, we have a, so we can plug in. But had you not had them, you needed to do some algebraic manipulation. Notice that this is an example of difference of two squares. Remember, difference of two squares is something like x squared minus 4. Well, that factors into x plus 2x minus 2. Or x squared minus, say, 25. That factors in x plus 5, x minus 5. So for these problems, if you have to go ahead and factor the numerator, you could do this. You could factor the numerator, and I'll put it on the note on the side as a note. The numerator could really become this. Okay? All over 2a is what equal to y. So we have Vf plus Vi and Vf minus Vi all over 2a. You could factor it, but we're not going to be doing that. Okay? So we don't have to worry too much about that. Let's go ahead and take a look at what we end up getting. So let's keep going through this process. We'll plug in. The final velocity is still 0. The initial velocity is still 25. Notice I kind of drop the units whenever I put a 0 in there. Technically, you should really write the units in there. Whenever it's 0, that whole part kind of drops off. Now, here's what you need to notice, though. 25 is squared, and then you do 0 minus that answer. So it's not negative 25 squared, which would yield a positive numerator. The numerator must be negative in this problem. It's got to be a negative numerator because the denominator is also negative, and we know that the y value in this problem is positive because the rocket moved upward. So here, what we're going to notice is we're going to have really 0 minus 625 all over negative 19.62. Okay, so it's a negative over a negative in the end. What you end up getting for the maximum height for this problem is 31.85 meters, or 31.9 to the nearest tenth. Alright, let's take a look at part C now. Let's take a look at part C. Part C says, what will its velocity be when it returns to ground level? Now there's two ways to solve this problem. When it returns to ground level, what will the velocity be? We could think of this as a free fall. I'll split it into two columns here. We can think of it as starting up here, the rocket, and it's a free fall to the ground. Because we know this height, right here, is around 31.85 meters. So we could say it's a free fall because it does pause at the top, and then it starts from rest in a sense. So we could say the initial velocity is 0 at the beginning. Okay, the y is negative 31.85, and we're looking for Vf. Or we could start the problem from the beginning and say, well, the rocket is going to go up to the top, it's going to pause for a second, but then it's going to come back down to the bottom and end up here. If we do it this way, now we have an initial velocity of 25 meters per second. But now the difference is that the y value is actually 0. Because if you start at the ground and the rocket launches and it goes up to the sky and it comes back down to the ground, it means there's technically no displacement. So y would be 0 meters. So let's solve this both ways here. Okay, let's solve this two different ways. Again, we're still looking for Vf, the velocity of the object right before it hits the ground. The impact velocity, we would call it. So on the left-hand side here, we'll notice that we have Vi, we have y, and we have Vf. and we're looking for VF. We also have the acceleration in both of these problems, and we're going to need to know that in order to use the correct equations. So what we'll see here is that we could start on the left-hand side first. We could say to ourselves, well, let's start with VF squared equals VI squared plus 2AY. The reason I'm doing that is because I don't know the full time of the trip. I know the time on the way up, but I don't know the time on the way back. We're going to figure that out in part D. For now, we know everything else. We know everything on the right-hand side. We know that the initial velocity, if we start as if it's a free fall, as if it's being dropped from rest, the initial velocity would be 0. So that just goes to 0. So we're left with VF squared equals 2AY. Over here, you'd have the same problem, or the same formula. But the one difference now is simply that y is 0, which makes this 0, which makes this whole term 0. So this entire term goes to 0 here, which leaves you with VF squared equals VI squared. Well, that's kind of intriguing to think about. So on the left-hand side, we get VF squared is just 2AY, but on the right-hand side, we get VF squared is the same as VI squared. Both of these are going to be right, so that's what we're going to try and prove now. We're going to take a look and see that both of these are correct. So on the left-hand side, let's go ahead and plug in. We've got VF squared equals 2 times negative 9.81 times negative 31.85. Notice I'm dropping units there just for simplicity. On the right-hand side, we have VF squared equals simply 25 squared. Well, that's kind of intriguing to think about. If VF squared is 25 squared, then VF must be 25. But here's the thing. You end up getting this. Oops. And then when you take the square root, you have to remember that you get plus or minus 25, actually. And that's an important part. And here you're going to notice the same thing. VF squared turns out to be approximately 625. So the same answer you get in each way. Well, the question becomes, which is correct? Is it plus or is it minus? And this is where you have to use logic. In the problem, the object is falling to the ground. So the final velocity has got to be negative. So our answer for this problem turns out to be that VF is negative 25 meters per second. And again, you can solve it using either method. Now let's take a final look at the last part, part D. Part D is off the screen, but I can read it. It says, how long will it take the rocket to return from its max height to ground level? And you might think right away to use symmetry because it took 2.55 seconds to get up to its max. It should probably take the same to get back down because we're assuming that air resistance is negligible. And we can do that and we can take a look. So in this case, we're trying to find t now. And now we know our final velocity. So we could say VF equals VI plus AT. Then from here, let's solve for t. So subtract VI, you get VF minus VI over here, and then divide by the A. That's what t is. So all we have to do is plug in now. The thing we have to notice, though, is that we're looking at the problem on the second half of the trip. So the rocket is falling to the ground now. So our VI is going to be 0, even though our VF a minute ago was negative 25 here. Okay? So what we end up getting for this problem here, when we look at it, we're going to have negative 25 minus the 0 all over negative 9.81. And that's the time it's going to take for the object to return to the ground from its maximum height. And what we'll notice here is that it turns out to be exactly 2.55, or the same answer as we had earlier for the time it takes to get up to max height. So what conclusions can we make from this problem? We can see that when an object is launched from the ground level, okay, from ground level, let me draw a picture of what I'm talking about. When an object is launched from ground level, it reaches a max height, and then it returns back down to the ground. The velocity it's launched at is going to be the same as the velocity it ends at, but they're going to be opposite signs. So we could say that their magnitudes are the same. Okay, the initial velocity and the final velocity, if you look at the whole problem, are the same. It was launched at 25, and it landed at negative 25, okay? So we're looking at their magnitudes. And we could also say that the time it takes to get to the top is the same as the time it takes to get to the bottom. The last example here says Jason is a viable so that it moves with an initial velocity of 6 meters per second straight upward. If the viable starts from 2 meters above the ground, how long will it be in the air before it strikes the ground? So here's your ground level. Here's Jason. Okay, let's say the viable is there and he's going to serve it. So the viable goes up, and then it returns back down, but it goes back down to the ground level. So it ends up down here. Okay, and we know that the height he's serving it from is about 2 meters above the ground. So what we're going to think about is this is your initial position right here. This is your final position. So even though it took this path, the overall displacement is just down from here to here, 2 meters. So we could say that y is negative 2 meters. We also know that the initial velocity was upward with 6 meters per second. We know the acceleration due to gravity is negative 9.81 meters per second squared. Turns out if we want to find the time in this problem, we can't use the first equation, Vf equals Vi plus At, simply because we don't have a final velocity. But we can use the equation that says y equals Vit plus 1/2 At squared. It's just going to be a little bit messy. Okay, we're going to have to use the quadratic formula. So let's go ahead and plug in. We've got negative 2. I'm going to drop my units here for sure, because I'm going to use the quadratic formula in a minute. Equals 6t plus 1/2 negative 9.81 t squared. Let's go ahead and make the numbers look a little neater. Half of negative 9.81 is approximately, or it is negative 4.905 t squared. Now, if we move the 2 over and rearrange it, we'll get 0 here. So we add the 2 over here, and then I'm going to switch the positions of these two, making sure to carry the negative sign here. So by carrying the negative sign, I have the negative 4.905 t squared plus 6t plus 2 equals 0. And we can see that this is a quadratic equation in nature. So we have to go ahead and use our quadratic formula. So we have t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now please remember that this is a, this is b, and this is c. And it's the numerical component only, it's the coefficient. So what we end up getting from that is as follows. T equals negative 6 plus or minus 6 squared minus 4 times a times c, let me extend this line, all over 2a. And the interesting part to note for this example is that we're definitely going to get 2 roots. And if we get those 2 roots, we get 2 times. We get a time of negative 0.27 seconds and positive 1.5 seconds. Well, we're going to reject this because it's a negative time, and that kind of correlates to the fact that it started 2 meters above the ground. It has to do with that starting value and the time it would kind of move back toward the ground. But this is our answer of 1.5 seconds. Your homework for this section is from section 2-3 on page 64 and 65.